Welcome to the academic session of this OSPM Summit. So I'm Tommaso Cucinotta. I'm from the Real-Time Systems Laboratory of Scuola Superiore Sant'Anna, which is a little university in Pisa, and where we used to host the previous editions of the OSPM Summit, as many of you know, as you were also there. And I'm also coordinator of the real-time systems area at the Redis Lab. This talk, basically, I took an opportunity to talk about some research we've been doing, to tell you about some research we've been doing on power management and optimizing power consumption in a couple of industrial use cases where we took inspiration from this AMPERE European project. So I'm going to tell you a little bit about the project and a little bit about the research we've been doing, some experimental results. So fundamentally, the project was about model-based engineering of high-performance embedded applications on heterogeneous hardware with real-time constraints and energy efficiency. We got a number of partners in this project, including, for example, Bosch and Thales, who provided two of the major use cases. But the project had also a real-time, let's say, handled real-time constraints, and as well as the idea of tackling a sort of HPC embedded applications where you need more and more computing power to do real-time stuff on embedded platforms. So the motivations are clear as we have cyber-physical systems that are becoming more and more powerful in computing power. We are also increasing the demands that are put on these systems from applications and services. So we want to do more and more with them, but also these platforms are becoming more and more cumbersome to handle because they are highly heterogeneous, including different multi-core CPUs with different, for example, CPU capacities for big latent architectures, or even GPU acceleration or tensor processing units, FPGA acceleration, and others. So the thing is, getting to use these platforms optimally is still like a specialty that very few manage to master while developing their real-time applications. And it's very often it's a trial and error process by which you try to implement something, then you refine, you double check the timing, see whether it works, see if you can accelerate more. And it's something that it's not really so smooth to get right. And there's an increasing interest in using platforms like this in the automotive, railways, aerospace, robotics, gaming, multimedia, and a number of use cases. So some of the challenges are these. So if you have a heterogeneous platform like this, which can even be battery operated in some cases, or anyway, you may have energy constraints or power consumption constraints. How can you optimally configure your hardware capabilities, like DBFS settings of the CPU, but also how can you configure your software in the sense, for example, of where do you map applications and processes into the available cores? So how can you decide whether to run applications on one of these cores or whether to deploy, I don't know, maybe a hardware accelerated version of a software function instead of deploying it in software? We may decide to deploy it on a GPU if we have a GPU accelerated version, or if we have an FPGA on the system, maybe we can hand over to the FPGA some of this functionality. So how to do this by keeping into account performance versus energy consumption trade-offs, real-time constraints, possibly even safety and certification constraints. And this is basically a sort of a hell. So this problem was tackled in this project by using a model-driven engineering approach, which is an approach that tries to fill the gap between high-level specification of systems with the actual system behavior at runtime by trying to automate as much as possible the as much as possible the various steps involved in a system definition. So the idea is that if you use some formal languages and models to specify your system from a high-level perspective, you couple it with some automatic code generators, then you can get basically two values. So one is from the high-level model of your system, you may get to analyze the properties of your system offline, and that allows you to optimize the system configuration. But also, if you can generate automatically code out of these high-level specification, you can also create very quickly a prototype that you can deploy on a real system to see whether the timing is actually correct as you are thinking of. So this can be done at early stages of the design when you don't have yet a complete implementation of your system to do some preliminary evaluation. And later on, you can switch to, put there, substitute your mock-up functionality, auto-generated functionality with real functions. Then you can double check, as things go by, you can double check you are still satisfying your real-time constraints, you are still doing well on your power consumption targets, etc. So MDE ideally aims at this correctness by construction, but I know it's very idealistic. So the idea is that you have all these tools to try to reduce this gap between all these steps in the software development lifecycle. So additional limitations of MDE approaches are that they handle often single processor systems, so they have very limited support for multi-core and struggle at coping with heterogeneous embedded boards as the ones I mentioned earlier. So that's why we needed this European project to handle this problem. And this was done by fundamentally bridging into classical MDE methodologies oriented towards the automotive use case domain, so where you use often things like AUTOSAR. I'm not sure if you're familiar with AUTOSAR standards, or AMPERE. There is the one we used in this project, which is a sort of open source variant of the AUTOSAR standard. And we try to expand. Of course, we are researchers, so we can do these things. So in AUTOSAR, every runnable is sequential, strictly sequential. That is one of the pillars. And we said in this project, wow, runnables can be parallel. Or a task in AUTOSAR that normally is an operating system tasks hosting sequential runnables. In this project, we made a little bit of, wow, a task is a dependency among computation stuff, which we can encode using OpenMP to ease programming, for example, for people working with OpenMP, with the parallel platforms. So the idea was to fundamentally stick parallel programming models into the software development life cycle, coupled with a design methodology based on AMPERE, and still keep this ability of having analyzability of the schedulability of the system to double check, all deadlines that are there can be verified, and to also estimate the power consumption of the platform, to optimize the platform actually to minimize the power consumption. Okay, so this is an idea fundamentally just high level of the set of tools we realized in this project. So just shortly speaking, we have a software architecture where we have a real-time hypervisor that is needed to handle mixed criticality workloads. So if we have hard real-time software to be run on the same platform where you want to run also some, let's say, software which has still important timing constraints, but is not safety critical, it's not as safety critical as, classic as is needed for with the hard real-time OS. Then we can fundamentally host on the platform a partitioning hypervisor. In this project, we used PikeOS, and we can have fundamentally a hard real-time partition which is a sort of virtual machine where you can host a hard real-time OS. In this project, we use the Erica Enterprise because we had one partner was Evidence. And on the other partition, you can put Linux so that you can take advantage of the, the great availability of software, libraries, multimedia, processing, options, even drivers, all the stuff you have on Linux that may be more difficult to find on a hard real-time OS. And in the software life cycle, we fundamentally have foreseen a set of tools that start from high-level models, and then we can fine-tune the models, but also we can automatically generate code, deploy it on the platform, see, profile what's going on in the platform, and try to refine the models after deployment, so that we can create a sort of cycle-based life cycle in which we can refine the model, so to get to the final system. All the time, verifying that the time predictability is there, that resilience is there, the needed energy efficiency is there, and all these properties we need. Okay, so just the two use cases we had in this project are from the railway domain. Thales has developed an obstacle detection and avoidance system, ODAS, that is being deployed, or at least as far as I know, is being planned to be deployed as a testing environment on the Florence tramway. And it is a system that helps the driver of a tram to understand whether pedestrians are going to cross and risk their lives under the tram on the railroad, or they will stay safely on the side of the road. As you can imagine, for a machine, this may not be so trivial. Of course, there's a human operator there, but as we know, humans may make mistakes, etc. So the idea is to have a system that augments the human senses by using cameras, so real-time streaming from cameras, and analysis, object recognition from the video camera streams, and also sensor fusion by crossing the information you're reading from the camera, what you're detecting from camera, from what you're detecting from sensors on the tram, from what you're detecting from the LiDAR that are on top of the tram. So there's this sensor fusion algorithmics, and in the end, we create additional alarms that can alert the driver in case he gets distracted, that there's a risk. And the other use case in the automotive domain is this predictive cruise control from Bosch, which is fundamentally an idea to optimize the speeding, the cruise control functionality by taking into account sophisticated knowledge on what's going to happen in the short future in terms of the terrain, format. So if we are going to see up hills or down hills or whatever, the car can optimize better the way it handles the fuel. So this is a software architecture and the hardware board we focused on. This is one of the two hardware boards we focused on. So which is a Xilinx ultra-scale ZCU102 board with Cortex-A processors and Cortex-R, which are the real-time CPUs, which, however, we didn't use actually for the experimentation we did in this project. So this is one of the platforms where we have the full software stack we envisioned in the project, with this hypervisor, Erica RTOS on one side, on one partition, a Linux kernel on the other partition, and there's a number of middleware there to let these two domains communicate with each other in a non-critical manner. So we have some even ROS-based and DDS-based middleware communications alongside other stuff. Okay, so end of the introduction to this AMPERE European project. So it's now I'm just going to tell you what we realized at our university in this project. So just I'm providing an overview of the major outcomes. So what we played with in this project was, as we are real-time systems lab, so we played with real-time system simulation, because in academia we are still willing to simulate stuff before implementing. So sometimes maybe it's easier to implement than to simulate, but we still simulate a lot. For students, it's a lot easier rather than getting started to put in their hands in the Linux kernel scheduler. You know something about it, but we made some extensions to a real-time system simulator to handle power awareness, thermal awareness, big little architectures, and we also gather this data on a number of different platforms. We also designed extensions to the constant bandwidth server for let's say, for a power aware in a power aware fashion. This extension was called Big Little CBS, and it's been tried fundamentally in simulation. But I'm telling you in a moment what it is. We played with some experimental changes to the deadline scheduler in the Linux kernel. So some of these, I'm putting there the disclaimer prototypes, so you don't think that I'm supposed to have done LKML submission. So this is playground for students. Apologies for that. Maybe some of these you may see an LKML submission, but maybe not. So I don't know. It depends on how hard Daniel looks at me. So depending on that. So one of these changes was this adaptive partition EDF that fundamentally tries to partition tasks scheduled deadline without API changes. So without changing to the interface, to the kernel interface, we just do partition EDF as much as possible. If, as we are in the multi-core worlds, we try to partition these tasks automatically in the kernel space with a very little overhead. And whenever it's not possible, we fall back to global EDF that is already there in scheduled. And this has improvements, has benefits on the way we handle DBFS in Linux, because the traditional way you schedule deadline, maybe you disable DBFS, you just run everything at max frequency. But here the idea is to leave the frequency variable, making such a way that we can host a real-time workload with the minimum frequency that is capable of hosting the workload without missing deadlines. We can do that with some tweaking of schedule TL. Gabriele will talk about that later, so I don't want to spoil too much his presentation, but this is one of the things we've been playing with. Also, we developed a theoretical framework for handling a little bit better the schedulability tests whenever we move CBS reservations. So in a dynamic setup where we move CBS reservations, we move them dynamically across cores, for example, for minimizing power dynamically, and things go by on the platform, want to keep minimum power. Then as we move reservations, we normally have to check how to you allow a new reservation on a core, normally when the schedulability limit is not violated, but actually we can do better than that with a very simple variant of the admission test. And that's something we developed, we studied theoretically with Luca, and we made some baseline simulations. But that is something that can be built on top of the APDF, for example. Then we played with some theoretical admission tests for APDF on Big Little. We handled this big challenging problem we had in the AMPERE project of how we handle this optimization of the software we want to run on a heterogeneous platform in presence of other accelerators and in presence of software that can be specified as real-time directed acyclic graphs. And we developed also a real-time framework that is an attempt to try to handle, the dual vision that we have in real-time systems. So either people go for fixed priority scheduling or for EDF priority scheduling. There's been a lot of papers comparing them. And these are like they became almost two religions. So there is on one side industry that uses only fixed priority so far. EDF scheduling is considered a little bit more a research playground at the moment. So the idea is that we have a framework where it's a user space framework where you declare as an application what you know about these real-time tasks you want to deploy. That's why we call it declarative. For example, I know only my rate of activation. I know only the rate of activation. Then the framework automatically does, okay, you know what? I'm taking a CPU, one of the available cores, and I'm deploying real-time tasks rate monotonic there. Then I have another task that comes and says, oh, I know my worst case execution time and my period, and I want to be scheduled precisely. And then, oh, here you go. I take another CPU core, and I schedule tasks and admit their tasks by sched deadline, using sched deadline. Or I can admit them using response time analysis with fixed priority. Or if I have a task that says I want to run at this priority, then okay, I take another core. I mean, there's plenty of cores out there, even in embedded systems nowadays. So our mobile phones have at least 8, if not 12 cores or something. So there's a lot of space to do this. So this is an interesting framework in which tasks declare the best they know about themselves. The framework tries to match these declarative requirements with what scheduling algorithms are available on the platform, and then automatically and adaptively partitions the cores so that you may have on a core fixed priority scheduling under RTA admission tests. On another core, you may have ADF scheduling under classical single CPU ADF schedulability tests. So in another core, you have more different things. So okay. So about the experimentation we did on Big Little. So this has been part of the Gabriele's PhD thesis. So we've been playing with measuring what are the power consumption experienced by a number of different workloads and different micro benchmarks on a few different boards. So these were some experimentation did with Diodroid XU on the XU3 on the little cores, on the big cores, Raspberry Pi 4, Zinc UltraScale Plus, and also we measure the power consumption we have when deploying these workloads at different in different configurations. So here on the x-axis you see the frequency. So there is the execution time goes down with the frequency, and the power consumption goes up with the frequency. And interestingly, some platforms show let's say linear behavior that from a research standpoint is not that interesting, because fundamentally when you have a linear behavior like this, it looks like you don't save much power if you keep things at a low frequency or if you keep things at a higher frequency. That doesn't make a difference, because the higher power you pay staying at higher frequency is comes back. I mean, it's reduced because you are also running for a shorter time. So when the model is linear, fundamentally we don't have really much of benefits in tweaking DVFS. So it's like really race to idle and end of the story, max frequency. It won't be. Instead, on things like Big Little, it makes a big difference, because there is this non-linear going off the curve. So that is where we gain. If we set a higher frequency and then we stop at a utilization here, basically we are wasting more power than what we would get at a lower frequency, which is what people are, I think they know very well about. Everyone knows very well about Big Little. So by the way, we did these measurements. Now the interesting thing is that Gabriele has amended this real-time system simulator, which we had called RTSim, by letting it become a power-aware real-time system simulator. So we can embed these behaviors into the simulator so that it can become a playground for people without having the hurdle to have to measure these again and again. And Gabriele knows that to get these measurements, let's say precisely, he spent several months in tweaking the scripts. And there is also a framework out there which is called ParProf, which is an open source framework which can be rerun on a different platform to try to get these curves for a different platform. So
yeah, I was curious, like, does this model CPU idle as well, or is it, because you mentioned higher frequency?
Yeah, very good point. Indeed, I didn't mention CPU idle because we don't have it. I mean, CPU idle states are not included in this analysis.
Because I imagine, like, even if it's non-linear at higher perf per watt, you'll still probably see there's some.
So sorry, I have to say CPU idle. Yes, we measured the power consumption also when the CPUs are idle. What I was saying that we didn't measure the deep idle states impact. So for example, if you manage to turn off all the CPUs of an island, then it makes a difference than keeping simply a CPU idle and the other CPUs computing. So this difference was not counted. But yes, we considered also the idle power. So we fundamentally, I mean, if you have a periodic workload running on a CPU with a given utilization, fundamentally the power consumption is the idle power plus the difference between the busy and the idle power times the utilization of the task or the utilization of the workload. However, in this study, we also consider that these curves may be different depending on the workload. That's why you have in here different curves that are related to computing hashes, compressing with gzip level 1, 5, or 9, encrypting, decrypting. Yeah, and also the idle is there. So did I answer your question?
Yeah, you did. Yeah.
Okay. So that's right. The idle curve is the idle. Yeah, it's there in the plots. But we neglected the deep idle that are another chance of saving power. So that. And yeah, so this is relatively okay. These look okay, manageable, these curves. But what happens if you look at scalability? So if I have only one core processing, or I have 2 or 3 or all 4 cores in an island processing, do things change? Yes, I mean, depends on the workload. So there are some workloads I'm showing there on the upper left. You see the flat lines on the bottom in the upper left plot. So those are workloads where the execution time doesn't change when I increase the number of tasks concurrently deployed on different cores, because these are fundamentally, probably they have a small working set size that they don't interfere much on the cache level. So they are relatively independent. So you deploy one of them, 2, 3, 4 on different cores. They don't care about each other, right? They can coexist without interferences. But look at the others. Those other tasks that are increasing linearly, they interfere a lot. So that means they are more data-centric tasks that are using more data. They are probably interfering on the cache level. So the more tasks you have, and the more the execution time of the single task on a single CPU goes up, because you are undergoing the interference from other tasks on the other system. So of course, these are phenomena that are not easy to model. And in some other cases, you can see there is even a sort of threshold case, like 1 and 2 instances stay well together. But if once I add the 3rd and 4th, then I crash the cache, and then I start probably trashing the cache, and I have a bump up. And also on power consumption, fundamentally, this reflects in the fact that the power consumption that I see for some cases is, let's say, ideal. I mean, 2 tasks bring twice as power than 1 task, and 3 tasks will triple the power, etc. But if tasks are interfering with each other, so they are actually being slowed down because of the interferences, so more cache misses, so more CPU stalling, waiting for data, etc., then the power consumption also curves bend accordingly, because they are not. So these are things that are relatively nasty and difficult to model in a real-time settings, in a real-time context. Okay, so some other thing we did in this simulation still is to model the thermal behavior of the cores. So we measured from real data the temperature of the individual cores. This is an example of a CPU cores of a Cortex A15, so a big core of the, I think it was the Odroid still here. So we measure what happens when we deploy something on one core or two cores or three or the cores. And this is how the temperatures basically go up in time when you deploy something. So we try to embed into the simulator this notion of thermal awareness that also keeps the time behavior of the temperature on the cores. And this is done with a simple thermodynamical model where we just put like when a CPU is idle, it has basically a little flame. When it is busy processing, it has a bigger flame, bigger heat, and this heat gets dissipated through some thermal resistance towards the environment, but also towards the other CPU cores. And this allows us to have a model that once it gets fitted, optimized on the real data we measured from this platform, we end up with these curves. You can see the smooth curves are the theoretical optimized curves fitted from the model, and the noisy ones are, of course, the real data getting there. And I mean, here you have just a few equations that come there, but it's a very simple thermodynamic model of the system. So again, what is the purpose? Again, is to have a simulation playground where, if you are a PhD student or something, you can start playing with this even without having the boards. You want to design a new scheduling algorithm that I don't know, keeps the CPUs cool, doesn't let us go beyond a temperature threshold. You can move stuff around, just to keep things cool, to not let them. I mean, you can play with this using the simulator, and then maybe later on you will buy some board and make some real experimentation. This big little CBS is simply a variant of the CBS for multi-core big little platforms where we try to, whenever, instead of applying a standard EDF scheduling, we try to still do a dynamic and adaptive partition scheduling of tasks on the available cores. So in this case, what we do is whenever a task wakes up, we try to host the task on the CPU where I would have presumably the minimum power consumption difference whenever adding this task. So I can either choose to keep the task where it is, on the same CPU island where it is, move it to a different CPU on the same island. I can, so normally these may imply that I may have to bump up the frequency of the island. This might possibly be done without bumping up the frequency of the island, or move to a different island because maybe it will be more power efficient. And we have in this experimentation both cases where it is even more convenient to wake up a task on a big core that is already running, it's already doing other stuff, rather than keeping it on a little core where it's already running. So anyway, we made some experimentation with this. This was experimented in simulation and with there's some theoretical work behind and some simulations only. We studied the admission test in these cases. So as the framework is very adaptive, so we fundamentally admit tasks, but then as soon as tasks go to sleep, we pretend tasks are no more there. Not immediately, we wait for the zero lag time. I mean, we do it safely from the real-time scheduling perspective, but then we say, okay, if tasks go to sleep, especially if they are sporadic, they are not periodic, but they are sporadic, you don't know how often they will come back. You only have a minimum interval period. So in that case, task goes away, you reduce power to save power, you reduce the frequency to save power. When it comes back, it will possibly be replaced into some other location, different core, different island, maybe. So in this case, the challenge is, can we make sure that no matter what is the order in which these tasks come, go to sleep, wake up later, can we make sure that we will always find a good spot where to deploy this task? Because it's not for granted, right? Maybe Now I'm accepting it, and it will fit into a CPU. Later on, I have the tasks scrambled, and it wakes up, and I cannot fit it anymore because situation is different. Oh, sure.
In which point do you make this decision to workplace at wake up time?
Where to place it at wake-up time.
Okay.
But the admission test we studied is when I accept it at the beginning.
Okay.
So the idea is that I can accept it only if I'm sure that no matter what, I will find a spot where it fits, satisfying the schedulability.
For a partition model.
Still for the adaptive partitioning
Okay.
case, yes. But you know, if you let's say one weak point of this model, which I have no problem in telling you. So one weak point, which probably connects better with the previous presentations we have seen already this morning, is that in these works, we sort of neglected the DVFS application delay. So whenever I bump up the frequency of the CPU, here I'm assuming that that may happen immediately or in a negligible time, or equivalently, I have tasks that are real-time. They have constraints, but they are not so tight so that, I mean, I can reason on a time scale that allows me to neglect this phenomenon. But let's say one way not to neglect it is to oversize the worst-case execution time, keeping into account that when a task is deployed, for a little amount of time, I can expect it to still run at the old frequency, and only later it will get bumped up. But in order to do that, I mean, we didn't really sort out all the details of the maths and how this needs to be changed. So for now, this, let's say, as a framework, works in simulation, assuming this zero time to bump up the CPU frequency, which we know is not very realistic. But so we have some nice future work. Okay, multi-criteria optimization. So back to the AMPERE context, as we have seen, the context there was a little bit more hard real time because there were these industrial use cases from automotive and railway. Here we dealt with the problem of how can I compute offline the best DVFS settings to host this real-time workload. So I have one or more directed acyclic graphs that are applications like this, where fundamentally each task starts only whenever its inputs are ready, are delivered. So each task is blocked waiting for all the inputs to be available. When they are available, the task processes the inputs and then it delivers the output to some other task. So we have a processing pipeline like this that can represent, I don't know, video processing, artificial intelligence for recognizing objects from a web camera, whatever you like, sensor fusion. And the idea is that there's an end-to-end deadline constraint here, which I should make sure that is not violated. So in a context like this, what we assume is that we know what are the worst case execution time as well as the average case execution time of the individual tasks when deployed on each possible CPUs I have on the system. So if I have a big little platform, I need to know what is the execution time on a big and the execution time on a little. If I have only one of the two, I apply the CPU capacity maths and I can get an estimate of the other, right? If I didn't measure all the execution times for all the frequencies, as we did in the other work I showed you, where we measured all the frequencies, well, you can make estimates based on models, right? But the idea is that, okay, once we have a table that tells me, okay, what is supposed to be the execution time of this task if I run it in software on this CPU at this frequency or this other CPU type on this other frequency, or what is its execution time when I run it, when I deploy it on this accelerator in case it's a hardware acceleratable task, if I deploy it on this FPGA hardware IP. And if I also know the associated energy consumption of running that task in that way, then I can build my optimization. I can build my optimization framework. So how do I do the optimization? Well, we did here is we played, we like Sched deadline, so we played with Sched deadline. This is from a paper, so you can read it. We got a question from the reviewers, why Sched deadline no fixed priority? And we answered them back, well, we like Sched deadline, we play with that. We like to play with that. I mean, we are Sched deadline people, right? So we have all the CPU tasks being deployed using a deadline, an equivalent EDF-based scheduling that can be done with Sched deadline, actually. Oh, sure.
Just curious. So you've got a system with many of these direct
Yes,
graphs
many of
in,
these.
many of these in. When you're trying to do your optimization, does that then therefore mean every single variant of where you could place all the tasks that are activated in parallel at once, you have to take all of that into account?
Yeah, you have to consider all the possibilities.
Everything, all the graphs, all the time, at each state where they line up.
But it's not at runtime. We do it offline. So
Okay.
the idea is in the workflow I showed you of the AMPERE project at the beginning. So early stages, you can do things offline, then benchmark. Okay, it's working, not working. I refine the model.
So you can do a simulation where you explore all the possibilities.
When explore, exactly, explore possibilities. But also we have both exact solvers for this problem and also heuristic solvers that run in orders of magnitude lower time, so we can even take best solution I can get in 1 minute, and then keep iterating, and maybe I can leave for the final stages of the system, of the software lifecycle. I can leave the fine tune.
Till right to the end.
Yeah. Towards the end, I do the full final optimization that would give me.
Okay, cool. Thank you.
Okay, so how did we explore? How did we do all this exploration of all the possibilities? Well, we use the classical way we do optimization nowadays, Cplex or Gurobi. I mean, in this case, the model is not very linear, so I cannot do a standard BLP, Boolean linear programming problem, so I cannot solve it with GLPK. I had to use a mixed integer quadratic or string programming problem. Just to tell you where the quadratic term comes from, because we had, as unknown in this problem, also the deadline. So the unknowns are the placement of tasks to processing units, so tasks to core, in which island, in which core, or even whether a task goes in hardware or in software, and these are Booleans. But I have also the individual partial deadline for the Sched deadline scheduler here. I leave it completely free to the solver to pick for me. So in the real-time scheduling literature is full of approaches for doing this, what is called the end-to-end deadline splitting, where I take a graph like this, and then I compute the individual local deadline, basically proportionally to how much work I have to do locally. But here we left it completely free for the solver to compute. And this gives me some advantages. So the nonlinearity comes from there. Now, skipping, of course, I'm not going to tell you, I mean, this is just to show you that we have this model and get to, okay, results. So fundamentally, the violet line is this mixed integer quadratic constraint programming approach that in this plot I'm showing that I'm able to host more task sets doing this, leaving these deadlines flexible. They are completely flexible. So in other approaches, all the other approaches, in all of them, I use a heuristic, the classical state-of-the-art heuristic to compute deadlines up front and then do the optimization. I mean, these may work similarly in a number of cases, but when I go to some higher utilization, then they fall short because they don't compute the intermediate deadlines optimally. Here I leave them completely loose, and I can host a number of additional cases. I manage to solve them. In those other cases, the other solvers will give me unfeasible. They don't know whether a solution can be found. So this is about how many tasks we can admit. And this is some real optimization. So on the x-axis, I have the computing power that I can achieve. On the y-axis, I have the optimization time that is needed. So in the mixed integer quadratic constraint programming is the green dots. that are, if you observe the clouds, they are, I'm the weather forecast man, sorry. So the clouds are a little bit more on the left side, the dots, because they achieve a better power consumption, lower power. But as you can see, the consumption time, the optimization time goes up, and notice the logarithmic axis. So we go from 1 second up to 10,000. And you can see here, this is a timeout I gave to Gurobi because I couldn't wait forever, of course, to do the paper. Sooner or later, you have to deliver the paper. You cannot wait days and days and days. So this is 10,000. Yeah, around probably a little bit less. Maybe it was 1 hour. This was a 1 hour cap, and this was 100,000, I don't know, maybe 1 day cap. And those are the heuristics we developed to make it much faster. So we have a much faster heuristic. The red one defines in fractions of a second, defines the optimal, suboptimal heuristic configuration. But you can see sometimes it gets higher power consumption. And this is actually, these errors are giving an idea of how worse solutions found by heuristics are compared to the optimum one. So the errors go roughly down and rightwards, because normally heuristic solutions corresponding to the same problem are solved in a much shorter time, but also with a worse power, with a higher power consumption in the final solution. So normally I move this on the right, but that gives an idea of how much I lose if I apply the heuristic in terms of optimality, but how much I gain in terms of waiting time of the designer. Okay, so I have plenty of stuff to say. One last thing, we can not only optimize for power consumption, minimizing power, but I can also optimize by maximizing the slack. That is another ability. As I told you, if I optimize only for minimizing power, then once the system has decided the optimum DVFS settings, then we leave the deadlines loose. That are, it doesn't have any reason to put deadlines, tighter or looser. So if I optimize for slack instead, then I will try to move the deadlines to, basically to leave as much slack as possible at the end of the DAG, so that I have some more robustness. As we are making all this experimentation on Linux, what happens is that normally the optimizing only for power, a few times we got some deadline misses. So in this case, these are on the X, the cases that have been optimized, they run on Linux. On the Y axis, 1 is the deadline. So we had a few deadline misses, but when we added the optimization also by maximizing the slack, then the solution was giving me a solution with the same power consumption, but actually with a better deadline settings that allowed me to not miss deadlines anymore. So these are the abilities we explored in this system. We also supported thread acceleration, but maybe I have no time to tell you about this. Just thread acceleration was the place where we needed to swap deadline and real-time scheduling classes to be able to handle fundamentally these additional work that has to be done on the background by the thread daemon server to handle it as a high priority interference. So this was more convenient for us than to set a reservation, a precise reservation deadline. So to model precisely the behavior of our thread daemon server for handling FPGA acceleration and reconfiguration. But if we configured it basically as a real-time task that runs on top of scheduled deadline tasks. It was configured as an interference so that we could account it in the usual inflation of execution times as you do for IRQs and other stuff. So that's it from my side. So thanks for listening. Bye.